Now let's take a look at 1435 here. So problem 14, 14, here we go, 1435. So, okay, so how do antibiotics work? So especially antibiotics versus bacteria, right? So a lot of these, work because, well, eukaryotes and prokaryotes use a lot of the same processes to make things work in their cells, but even though they're using the same processes, the proteins to do those things are slightly different. And this is true for translation, right? So we talked about the ribosomes in prokaryotes and eukaryotes. So we have this small subunit here, and let's say that is from prokaryotes, and we have a small subunit from eukaryotes here. And before I go on, I wanted to mention, in the last video I mentioned it, but I wasn't sure I had the location right, but our closed captioning, if you're interested in closed captioning, and we're not using, and you can use the automated ones from YouTube, but we have people actually working on these from the Student Access and Accommodation Services Department of Illinois State University, so we need to thank them for the closed captioning. And sometimes I talk really fast and mumble, and so I imagine it must be pretty difficult to put those transcripts together. So I thank them, and even if you don't really need to use them normally, they may help you, especially if I'm not speaking directly into the microphone or if I'm talking a little fast. So we thank them for the transcripts. Now, okay, where were we? We were talking about ribosomes in prokaryotes versus eukaryotes. And here's our small subunit here. And let's see if I can remember these without my notes. I'm going to call that the 30S. And this is a 40S subunit. And these are the ribosomes in prokaryotes, and these are the ribosomes in eukaryotes. Okay, so that's the small subunit, and we also have a big subunit, right? So big subunit, and this is going to be the E site, this is the P site, this is the A site when these come together, right? So same thing over here. I think my ribosomes looked better in class. These look terrible. But we get the point. There's a large subunit and a small subunit. So 30S for that, and remember S is Svedberg unit, and it's based on the rate of sedimentation during centrifugation. So Svedberg. And the whole ribosome is going to be 70S, and because these are rates of sedimentation, these, you don't just get 30 plus 50 to make 80, right? Because they're not, you don't add them, they don't work like that. So the whole subunit, the whole ribosome sediments at 70 Svedberg units, not 80. However, for the eukaryote here, ribosomes in eukaryote, we have 40S for the small subunit, we have 60S for the large subunit, and the whole ribosome is an 80S. So now, some of these antibiotics that we use to, keep ourselves healthy, and when we get sick and we have a bacterial infection, these antibiotics, why do they work? Say we have our body full of bacteria, and we're undergoing an infection, or you have a wound somewhere. You need to take antibiotics, and these antibiotics often work because, they bind, a prokaryotic ribosome, or part of it, and the eukaryotic ribosome is slightly different. So both prokaryotes and eukaryotes need translation to survive, and if you turn off translation, well then in the prokaryote's going to die. Same thing for the eukaryote. But so in problem 14, where are we? 1435, we have a table here of different antibiotics. Let me see. I lost it. Okay, I got it back. Let's see. Table of antibiotics here. I'm going to copy that, and I'm going to try and paste it in over here. And, okay, so here's the question. Or let me just read the question. So, the emergence of antibiotic-resistant strains of enterococci and transfer of resistant genes to other bacterial pathogens have highlighted the need for new generations of antibiotics to combat serious infections. To grasp the range of potential sites for the action of existing antibiotics, sketch the components of the translation machinery, and then it's saying, for example, see step 3 of figure 14.6. I don't think we need to take a look at that. Okay, so in using a series of numbered pointers, indicate the specific location for the action of the antibiotic shown in the following table. Okay, so here's the table right here. And we're going to show where these antibiotics work. Okay, so we have a bacterial infection, and our doctor, prescribes streptomycin. And I hope some of you are doctors someday, and you treat me for free. That would be nice. No, I'm just kidding. You don't have to do that for me. Okay, so let me see here what kind of pointer we want to use. Okay, so let's look at streptomycin. We have an infection. Our doctor prescribes streptomycin. So streptomycin binds to the 30S ribosomal subunit. So streptomycin is going to, we're gonna take streptomycin as a pill or liquid or chewable. If you're like me, you don't like to take pills. So streptomycin is going to come in here, and it's going to bind to that subunit there, and it's going to inhibit translation of the proteins inside the bacteria, and the bacteria aren't going to be able to divide. Okay, so this is going to help us fight off that bacterial infection. So 1 goes there. So chloramphenicol. Okay, so we want to, let's say we're using chloramphenicol now. We're allergic to streptomycin, so we need another antibiotic. So chloramphenicol inhibits peptidyl transferase of the 70S ribosome. So the whole ribosome, when it's completed, and transfer RNAs are coming into the A site here, and they're shifting over this way as the messenger RNAs are being translated. The peptidyl transferase, that's the thing that transfers the amino acid that's attached to the transfer RNA in here, the growing peptide chain right here, transfers it over to the other amino acid that was in the A site. That was on the transfer RNA in the A site. Okay, remember all that stuff kind of happens at the same time. So it's a little confusing. But anyways, chloramphenicol inhibits the peptidyl transferase. So it's going to bind somewhere in here. Okay, so tetracycline. Let me use a different color. Tetracycline inhibits binding of charged tRNA to the ribosome. So where does the charged tRNA go? Into the A site, right? Okay, so tetracycline is going to bind in there. And remember, so these antibiotics just bind really well to all of these components in the bacteria, not so well, to the eukaryotic equivalents, which is why we could take them. Erythromycin binds to free 50S particle and prevents formation of the 70S ribosome. Okay, so erythromycin is just going to bind to the 50S here, so and keep this 50S and 30S from coming together for translation. And I've never even heard of kasugamycin. Wow, that might be a new one. So kasugamycin inhibits binding of tRNA-FMET. And remember that? So tRNA-FMET, this is the special transfer RNA for initiation of translation. So this is the tRNA that is used for initiation of translation. So maybe this one binds directly to these tRNAs, or maybe it binds to the P site here to prevent that tRNA FMET from getting into that P site and helping initiate translation. So normally that'll bind up here, right? This is how we went over. The initiation of translation starts with that tRNA FMET binding to the small ribosomal subunit, and then the large one coming in. In thiostrepton, that one sounds pretty cool. So that prevents translocation by inhibiting EFG. Now, we didn't talk specifically about EFG, so elongation factor G. We kind of talked about elongation factors in general. We talked a little bit about EFTU and how EFTU is in charge of bringing the new transfer RNAs, charged transfer RNAs, into the A site. So EFG actually helps with that process too, or with elongation, especially with the translocation parts. So thiostrepton could either bind directly to EFG, or it could bind somewhere to the ribosome wherever EFG works. So let's just go with thiostrepton somehow inhibits EFG. Maybe it interacts directly with it, or interacts directly with the site that EFG interacts with on the ribosome. Okay, so that was a fun question, right? So now you know a little bit about how antibiotics work, and what about antibiotic resistance? You know, the question didn't talk much about that, so that, you know, kind of missed a good opportunity, I think, unless that's what they're going to talk about with in the next problem in 1436. But I'll just touch on it here. So let's say with let's just go with streptomycin right here. So streptomycin binds to the 30S ribosomal subunit. So one way bacterium could gain resistance to streptomycin would be just to, you know, change the proteins involved with forming the 30S, the sequence of the proteins or the ribosomal RNA involved with forming that 30S subunit. They could just change it slightly without interfering with the function of the 30S subunit, but preventing binding of streptomycin. Well, then that would be a bacterium that would be resistant to streptomycin. And so just by slight mutations or changes to the amino acid or even ribosomal RNA sequences used to build these components, you could interfere with the ability of the antibiotic to bind to these components and inhibit translation. So fairly easy for some of these bacteria to gain resistance to antibiotics, which is why we're always looking for new antibiotics. Okay, so now I'll go on to the next problem, which I think is about, I'm reading right now, the development of antibiotic resistance. Okay, so let's take a look at that.